Okay, joint distributions, joint random variables tell us how more than one random variable relates to one another. And one particular kind of relationship between random variables, a common one that we see is the assumption or the relationship of independence. We've seen what it means earlier in the course for two events to be independent. We haven't yet defined what it means for random variables to be independent because we haven't talked about the joint distributions until just now. But essentially, when we think about the distribution of a random variable, so just note that the distribution of a random variable x is determined by events of the form the event that x is in B for all suitable subsets B in the real numbers. In other words, it's determined by probabilities, all of these probabilities, right? So each of these is an event. And so two random variables are events, or two random variables are independent if their behavior, if all of the events determined by those random variables are independent. Okay, so definition of independence. X and Y are independent if for all subsets of R, the joint probability that X is in A and Y is in B is the product of the probabilities. Okay, so that's definition of independence. And now let's suppose that we have two random variables that are independent. I'm sorry, we would write, so we write X dependent of Y to denote that X and Y satisfy this definition of independence. And now let's suppose we have independent random variables with respective densities fx, fy. Then bring this down here. For all x and y, we can consider what's the probability that x is within a small window of little x and big Y is within a small window dy of little y. Well, we've done this before. We've played this game before, and we know that on the one hand, this is how we can think of the joint density of X and Y. Right? And on the other hand, so we know by independence, this is the probability that X falls within dx of little x times the probability that Y does. And we've done this before. This we evaluate as fx dx. This is fy dy. So we see that the joint density is the product of the marginal densities in the case of independence. So X and Y has the joint density given by product of the marginal densities. Conversely, it's true that if X and Y has a joint density that can be expressed as a product, then for any X, for any A and B, subsets of R, probability that X is in A, Y is in B. Well, here we're given the joint density, so this is integral, right? Double integral, as we've seen before. But the joint density is the product of the densities. Okay. But we can separate these because one only depends on, part of it only depends on X and part of it only depends on Y. So we can separate them out into the part that depends on X and the part that depends on Y. But when we do that, we realize, well, this is just the probability that X is in A times the probability that Y is in B. Which implies that X is independent of Y. So if X is independent of Y, then their densities are a product. And if the joint density is a product, and if the joint density is a product, then we can conclude that X and Y are independent. So those are equivalent. So we'll see independence come up quite a bit. We'll also see cases where random variables are not independent. And so it's important to understand the difference.